Hi, my name is Tan Ching Sen. I am from University Malaysia Police, UNIMAP. I represent about NMK 31103 antenna and propagation for my assignment 1B. Okay, I am from Faculty of Electronic Engineering and Technology, program UR 6523008, Design Telecommunication. Okay. What is antenna? An antenna is a transducer which convert electrical power into electromagnetic wave and vice versa. An antenna can be used either as a transmitting antenna or a receiving antenna. So a transmitting antenna is one which convert electrical signal into electromagnetic wave and radiates them. So the next one is a receiving antenna is one which convert electromagnetic wave from the received beam into electrical signal. In two-way communication, the same antenna can be used for both transmission and reception. So the example of the transmitter and receiver means two-person communicating. Okay, so one will be sending information, then the another one will be received. Then same goes to from receiver to the transmitter. Okay, then this is the example of antenna figure of antenna design. Okay, so in this assignment, I have been choose for the three antenna classification, which is the first one, microstrip patch antenna. So the characteristic is low profile, lightweight design, suitable for application where size and weight are important factor, commonly used in wireless communication systems such as Wi-Fi, Bluetooth, and RF. So the radiation pattern, a broadside radiation pattern with maximum radiation perpendicular to the patch surface. So the pattern is usually omnidirectional in the plane of the patch. So the antenna gain is typically range from 4 dBi to 12 dBi depending to the design and the size of the patch. So the application normally is wireless communication system, satellite communication, then RF system and mobile device. The second antenna is Yagi-Uda antenna. The characteristic is directional antenna with high gain and good front to back ratio, composed of multiple elements, including a driven elements, reflector, and director elements. So it provides high directivity and narrow bandwidth, beamwidth. So suitable for long distance communication and point-to-point communication. So the radiation pattern is normally directional radiation pattern with a main lobe in the forward direction and reduced radiation in the other direction. So it provides high gain and good front to back ratio, enabling efficient communication with distant stations. So the antenna gain will be in range from 6 dB to 20 dB, depending on the number and arrangement of the element. So the application, television broadcasting, point-to-point communication, long-range wireless communication, radio, and Wi-Fi signal posting. And the third antenna, spiral antenna. So the characteristic is compact and lightweight design, wide frequency bandwidth, suitable for application where circular polarization and wide angle coverage are required. So often used in satellite communication, wireless system, and RF system. So the radiation pattern is a conical radiation pattern with good axial ratio and circular polarization characteristic. So it provides a wide angle coverage and is well suited for application where signal propagation requires omnidirectional coverage. So the antenna gain, it's range from 5 dB to 9 dB. So it depending on the size and the number of turns in the spiral. Application, satellite communication, wireless communication system, and radio astronomy, RFID system, and mobile device. Okay, so this is the table of comparison, characteristic table of the three antenna, microstrip patch antenna, spiral antenna, and Yagi-Uda antenna. So the characteristic and radiation pattern and antenna gain are mentioned in the table. So for microstrip patch antenna, low profile, lightweight, and radiation pattern will be omnidirectional, the gain between 2 dB to 16 dB. So for the spiral antenna, compact, lightweight, and circular polarization, wide angle coverage, with gain between negative 17 dB to 9 dB. And the Yagi-Uda antenna, directional, high gain, and is highly directional, the gain is between 6 dB to 20 dB. Okay, so in my assessment, okay, I will be set the antenna specification. So the operation frequency will be 900 megahertz, distance from 1 kilometer to 20 kilometer, height of the transmitter 150 meter, height of the receiver station is 5 meter, and the power transmit will be 30 dBm, gain of microsweep patch antenna is 2.8 dB, gain of Yagi-Uda antenna 6 dB, and the gain of spiral antenna negative 15 dB. Okay, so I will be use the Hata Okumura propagation model. So this is the uh, formula of the propagation model. Okay. Okay, so the first one is power budget of environment 1, urban. So this is the coding and the output graph. Okay, then the second one will be suburban. So this is the coding and the output graph too. And the third one is rural. So the coding and the output graph also mentioned in the slide. Okay, so the next is the free space path loss. Figure above show the damping in free space FSPL for different frequencies. So it can be seen that the signal is already considerably attuned within a few meters from the transmitter, and that the attenuation increase with the increasing frequency. Okay, the damping attenuation increase with distance and frequency, so the signal is attuned along the direction of propagation. So in the graph, in the figure, we can see the different frequency, which is 2.4 gigahertz, 5 gigahertz, and 60 gigahertz. Okay, so why we need free space path loss? Free space path loss is a measure of how much a wireless signal weakness as it travels through the air over a distance. It increases with distance and frequency. It tells us how much signal strength we lose just because of the distance. On the other hand, the receive power is actual strength of the signal that receiver pick up. It depends on factors like the power sent by the transmitter, antenna quality, and the distance. If we calculate the receive power using free space path loss, the result will be lower. This is because the free path loss represent the weakening of the signal due to the distance. So when we divide the transmitter power by the loss, the receive power will be reduced. Okay, so this is my power budget FSPL, the output graph, and the coding. Okay, so the comparison of each environment with the free space path loss. Okay, the first one is urban area and free FSPL, free space path loss. Then the second one will be suburban and free space path loss too. Then this is the third one, comparison receive power in rural area with the free space path loss. Okay, so we can see that in this four figure, we can see that there are different output waveform. So typically will be 4 different wave. Okay, so in urban area, the power received is generally high due to the better infrastructure and shorter distance between the transmitter and receiver. So suburban areas have moderate receive power, benefiting from reasonable transmitter power and antenna gains. However, rural areas experience weaker receive power due to longer distance and limited infrastructure, compounded by the low antenna gain. Okay, so the free space path loss calculation help estimate signal attenuation over distance and antenna gain selection, such as using Yagi-Uda antenna is cure for mitigating path loss and maintaining better receive power. So overall, optimizing the power budget with suitable antenna choice is essential for reliable wireless communication across various settings. Okay, so in summary, I have made the different factor of the which can impact the receiver power and path loss. Okay, so there are 4 factors. First one is distance, second frequency, then the third one propagation environment, and the antenna gains. So in the table, we can easily see that the distance will be impact on on receive power and impact on path loss. So if the distance is increased, then the receive power will be decreased. Okay. And for the path loss, if the distance increase, the path loss will same goes increase. Okay. Then for the frequency part, if the frequency is high, then the receive power will be low. Okay. Will be high loss lah. Then if the for the path loss, if the frequency is high frequency, it will impact higher path loss. Okay. So the third one, propagation environment. More obstacle, then it will be higher loss. Then if for propagation environment impact on path loss is same, more obstacle, then it will be higher path loss. Then the last one is antenna gains. If high antenna gains, then the receive power will be higher. But if the antenna gains is high, then the path loss will be low. Okay, so this is the summary table and few of explanation. Okay, so I didn't go one by one. I just mentioned just now as the table, so we can see that the distance, frequency, propagation environment, and internet gains, it will impact on receive power and the path loss. Okay, so that's all for me. Thank you.